So this is just a brief overview of what you can do with the simulations when it comes to loudspeakers. Of course, you can use simulations for many things, but if you look at the screen here, you have a two-way speaker, a CAD geometry, and it's including everything. So all parts of the tweeter is there, all parts of the subwoofer is there, the cone, the spider, surround, everything, including the air inside of the tweeter. You can see the voice coil, everything is there. So with simulations, you need this CAD foundation. That's your starting point. Once you have that, you import it into simulation software. In my case, I use COMSOL Multiphysics a lot. I've used it a lot for loudspeaker simulations. I've used it a lot for many other simulations. And you can see I've imported the geometry here, and it looks exactly like it does in the CAD software. So what you need to do now is to figure out your material properties, which can be extremely difficult. So for each of these parts here, you need to know what is my stiffness, what's my Young's modulus, what's the density, that's fairly easy to figure out, and what's the Poisson ratio. And also you need to know for a lot of the materials, what is the damping. So we have these 4 parameters for each part that you need to know. Starting out, this can be extremely difficult, but if you imagine you work at one loudspeaker company, it's often the same materials being used again and again. So once you've been through this once, it's not necessarily that difficult to do the next speaker. So in that case, you only need the updated geometry. But certainly materials can be difficult to figure out. Then you need to set up the physics. The simulation software only knows the geometry for now. You need to assign different physics so that, for example, this cabinet that we have introduced here, we need to tell the software that this is structural mechanics and what are the material values for that. Same goes for pretty much all of the other parts, except for the air part in red here, and we have air inside the tweeter too. And that needs to be included to have the effect of the compression rarefaction of this air domain. There are other ways you can include it if you don't want to calculate explicitly. But in this case, I've included it. For these 2 domains, you need to assign acoustics as the physics. And then, as you can see, they couple. If we zoom in on this corner, you can see you have a structure and you have air. And the software needs to know that there's a coupling between the 2 because they each push on each other. In COMSOL Multiphysics, it's fairly easy because it knows how to do this coupling automatically. You only have to do a few clicks, and then all of that is included. So in principle, what you have is a full loudspeaker, and everything you could measure in real life with a physical model, or let's say a real loudspeaker, you would be able to recreate in this virtual lab, as you can call it. And that's all fine. I wouldn't recommend doing it on a full loudspeaker like this unless you have a fairly good computer. You should at least be happy with each component on its own. So you should investigate the tweeter on its own, the subwoofer on its own, and then in principle you could plug it in to a cabinet. But it's a fairly expensive computation. It's gonna take quite some time to calculate. You need a lot of RAM. On the other hand, if you really want to know what is the output from this combined setup, you would have to measure it, meaning you would have to build it, everything needed to be physically available. and then you would go to an anechoic chamber or something. Whereas here you can have a virtual driver that hasn't been built yet, but you can investigate it. You can see, okay, my response doesn't look that great. I need to do something about the surround or whatever it is. So typically you would look at one driver at a time. So that could be, let's take the tweeter, for example. So here it's a tweeter done in 2D axis symmetry. So we have assumed that the tweeter we saw before has axis symmetry, and that makes the computation a lot easier. So here we can, we've set up all of the materials, we have the geometry, we run the simulation. So what we have done is run a frequency sweep. So that's like what you would measure with a sweep, or however you do it with a chirp or whatever. But the result is a certain sound field at distinct frequencies that you have selected. And with this, you can animate whatever you want. You can go to player here. We can select a certain frequency. In this case, it's 15K. And then we can see what's the sound field outside of the tweeter, which is probably most relevant, but also inside. Perhaps you have some ferrofluids that affects the field you're interested in seeing that. Perhaps you want to see if you should put some foam in here. All of that can be investigated. And you can see we have a really exaggerated view of the dome here. And that's sort of what you have to do, because in these frequency sweeps, actually nothing moves. Everything is linear, so nothing moves away from a certain starting position. So that can sometimes mess up engineers a little bit. But you have to know what you're doing and what you're seeing on screen. And so you can plot like the frequency response. I'm not actually sure what I'm showing here. Yeah, it's actually a phase I'm looking at. But you can plot sound pressure level. You can plot power radiated in a certain across a certain surface, things like that. And again, you can do the same thing for the woofer and see that resulting sound pressure level from the woofer on its own. And if you want to, you can apply a crossover if you know the transfer function. You can apply the crossover as an active one, so you just multiply a known, let's say, Linquist-Riley second order transfer function upon the initial voltage input. So you've already compensated for that crossover. You can also apply a passive crossover. You can actually go in and make a network list, a net list, where you select certain components. In this case, I already have some components here to take into account the electromagnetics. So the Thiele small parameters are in part in here, but I could add more and have a passive crossover incorporated already. So all I would need to know, if I know all of the materials and the geometry, is to input a voltage. So it's very similar to what you do in the physical world. But you get more insight. You can see things that you wouldn't be able to measure because you can simply not get a probe inside, let's say, the gap here, whatever it is you're trying to see. So you get more information, but it can be tricky to set up, and you need to understand the underlying physics and mathematics. Yeah, so that's basically it. I just want to mention also that once you have this model, you can apply other things on top of that. That could be phase decomposition, like you have on your Klippel posters. Meaning, if you see something like this, you see a dip. This is a blog post I have here where I had a client who bought the phase decomposition product, and he used it for investigating a certain loudspeaker. He saw there was a dip, and with the phase decomposition, he could see that it actually came from the surround, and actually the whole um, cone setup with the surround being in quadrature, meaning it has movements that do not add uh, to the overall sound pressure. So a lot of the movement simply goes into nothing, and you have some in-phase pressure coming mainly from the surround. So that's what's giving the pressure you actually have. And you can have other dips showing up that are due to, let's say, the surround being in antiphase with the rest of the cone. So with simulations, you can apply things that you may also have in measurements, like the Clipper system has this built in, but that's for measured results. This is for simulated results. And you can use that to improve your loudspeaker. So here he ended up with a much smoother response. So the simulations themselves don't tell you exactly what should be changed. Maybe it shows you which parts are problematic, but you still need that engineering approach to figure out, okay, I see there's a problem with my surround being in antiphase or whatever, but what should I do about it? So there you need to try out different things. Maybe you have some ideas. And you can also apply optimization for some of these cases, but that's more complicated. So I hope this gives a little insight as to what you can do with simulations in general and specifically for loudspeakers. So that's all from me for now.